Compositions of exponential generating functions. The compositions of exponential generating functions can be defined in the same circumstances and in the same way as those of ordinary generating functions. In this subsection, we will see that the corresponding versions of theorem 8.13 for the ordinary generating functions and 8.15 also hold. Theorem 8.24, the exponential formula. Let an be the number of ways to build a certain structure on an n-element set, and assume that a0 is equals to 0. Let hn be the number of ways to partition the set n braces into an unspecified number of non-empty subsets, then build a structure of the given kind on each of these subsets. Set h0 equals to 1. Denote by a of x and h of x the exponential generating functions of these sequences. Then h of x is equals to e to the a of x. Proof. As in a set partition, the order of flux is irrelevant. It follows from theorem 8.21 that a of x to the k over k factorial is the exponential generating function for the number of ways to partition n braces into exactly k subsets, then build a structure of the given kind on each subset. Summing over all k, we get the summations of a of x to the k over k factorial, summing for all k which is greater than or equals to 1. As a0 is equals to 0, none of the power series a of x to the k over k factorial has a constant term. On the other hand, h of x has a constant term 1 by definition. This shows that h of x is equals to 1 plus the summations of a of x to the k over k factorial, summing for all k which is greater than or equals to 1. If we combine the terms of 1 into the summation, that will be the summations of a of x to the k over k factorial, summing for all k which is greater than or equals to 0, because 0 factorial is equals to 1, and a of x to the k is equals to 0 to the 0, which is equals to 1. So we can just absorb the term 1. So which is equals to e to the a of x. Example 8.25. In how many different ways can we arrange n people into groups and then have each group sit at a circular table? Solution. There are k minus 1 factorial ways to form a k member group to sit at a circular table. Therefore, keeping the notation of theorem 8.24, ak is equals to k minus 1 factorial. This yields that a of x is equals to the summations of k minus 1 factorial times x to the k over k factorial, summing for all k which is greater than or equals to 1, which is equals to the summations of x to the k over k, because we cancel out the k minus 1 factorial with k factorial. So now the denominator only has k. If we summing for all k which is greater than or equals to 1, then after the summation, that will be the ln of 1 over 1 minus x. Therefore, the exponential formula implies that h of x is equals to 1 over 1 minus x, which is equals to e to the ln of 1 over 1 minus x. And the e can cancel out of the base of the ln, which is equals to 1 over 1 minus x. And by the Taylor series, which is equals to the summations of x to the n, summing for all n which is greater than or equals to 0, which is equals to, if we take the n factorial into the numerator and the denominator, there will be the summations of n factorial times x to the n over n factorial, summing for all n which is greater than or equals to 0. This shows that there are hn which is equals to n factorial ways to arrange our n people around the circular tables. The reader should try to find an immediate combinatorial proof of this result. The following is an example of combined applications of the product formula and the exponential formula. Example 8.26. Find the exponential generating function f of x for the sequence Fm braces that denotes the number of partitions of m braces into blocks of size 3, 4, and 9. Solution: let An, Bn, and Cn denote the number of partitions of m braces into blocks of size 3 only, size 4 only, and size 9 only. And let a of x, b of x, and c of x denote the respective exponential generating functions. We will determine these exponential generating functions by the exponential formula. To that end, consider the following very simple sequence. Let Tn be the number of ways an n-element set can form a block of size 3. Obviously, T3 is equals to 1, and Tn is equals to 0 if n is not equals to 3. Thus, the exponential generating function of this sequence is t of x is equals to x to the cube over 3 factorial. It then follows by the exponential formula that a of x is equals to e to the t of x, which is equals to e to the x to the cube over 3 factorial. And analogous argument shows that b of x is equals to e to the x to the 4th over 4 factorial, and the c of x is equals to e to the x to the 9 over 9 factorial. Now let us split n into 3 possibly empty subsets and take a partition with blocks of size 3 on the first subset, a partition with blocks of size 4 on the second subset, and a partition with blocks of size 9 on the third subset. Then the product formula shows that f of x is equals to a of x times b of x times c of x, which is equals to e to the x to the cube over 3 factorial plus x to the 4th over 4 factorial plus x to the 9 over 9 factorial. Theorem 8.27, the compositional formula for exponential generating functions. Let An be the number of ways to build a certain structure on an n-element set and assume that A0 is equals to 0, let Bn be the number of ways to build a second structure on an n-element set, and let B0 is equals to 1. Let Gn be the number of ways to partition the set n into an unspecified number of non-empty subsets, and then build a structure of the first given kind on each of these subsets, then build a structure of the second kind on the set of the subsets. Denote by a of x, b of x, and g of x the generating functions of the sequences an braces, bn braces, and gn braces. Then g of x is equals to b of a of x. Proof: let us assume that we partition n braces into k subsets. Then there are bk ways to take a structure of the second kind on the k element set of these subsets. Therefore, it follows from theorem 8.21 that bk times a of x to the k over k factorial is the exponential generating function for the number of ways to partition n braces into exactly k subsets, then build a structure of the given kind on each subset, and then take a structure of the second kind on the k-element set of these subsets. As a0 is equals to 0, none of the power series bk times a of x to the k over k factorial has a constant term. On the other hand, g of x has constant term 1 by definition. This shows that g of x is equals to 1 plus the summations of bk times a of x to the k over k factorial, summing for all k which is greater than or equals to 1, which is equals to bk times a of x to the k over k factorial, summing with all those k which is greater than or equals to 0, which is equals to b of a of x. Example 8.28. We have n distinct cards. We want to split their set into non-empty subsets so that each of them contains an even number of cards. Then we want to order the cards within each subgroup. Finally, we want to order these subgroups into a line. find an explicit formula for the number of ways Gn, we can do this. Solution: keeping the notation of theorem 8.27, we see that an is equals to n factorial if n is greater than or equals to 2 is even, and an is equals to 0 if n is odd or n is equals to 0. Moreover, Bn is equals to n factorial for all n which is greater than or equals to 0. Therefore, b of x is equals to the summations of an times x to the n over n factorial summing for all n which is greater than or equals to 0, which is equals to the summations of x to the n summing for all n such that n is greater than or equals to 2 and n is even, which is equals to x squared over 1 minus x squared. And b of x is equals to the summations of bn times x to the n over n factorial summing for all n which is greater than or equals to 0, which is equals to the summations of x to the n, just simply summing for all n which is greater than or equals to 0, which is equals to 1 over 1 minus x. Therefore, by the composition of formula, g of x is equals to b of a of x equals to 1 over 1 minus x squared over 1 minus x squared, which is equals to 1 minus x squared over 1 minus 2x squared, which is equals to 1 plus x squared over 1 minus 2x squared, which is equals to 1 plus x squared times the summations of 2x squared to the mth, summing for all m which is greater than or equals to 0, which is equals to 1 plus the summations of 2 to the m times x to the 2m plus 2, summing for all m which is greater than or equals to 0. So the coefficient gn of x to the n over n factorial in g of x is 0 if n is odd, and 2 to the n minus 1 times 2m factorial if n is equals to 2m, which means that n is even. Consequently, for even n, there are gn which is equals to 2 to the n minus 2 and 2 to the n over 2 minus 1 times n factorial ways to proceed. Note that n factorial is separated from the exponentials of 2. That is, gn is equals to 2 to the exponential part is n over 2 minus 1. Then, after the exponential, we take n factorial ways. Note, the theory of generating functions is certainly rich enough to be the subject of several books. A classic in that area is Generating Functionology by Herb Wilf. For a far-reaching analysis of exponential generating functions, we recommend Enumerative Combinatorics, Volume 2 by Richard Stanley.